this lesson, we are going to review the content of our first unit, which dealt with techniques of integration. So the questions on this review are pretty similar to your first exam. So you have to go back to that exam and look at all of the integration techniques that we were given. So the first one that we discussed was integration by parts. And this was the reversal of the product rule. And the formula we used said that the integral of u dv was equal to uv minus the integral of v du. And usually you choose u to be something that will go away if you take repeated derivatives. So in the case of this particular example, we're going to let u equal x squared. And we will let dv equal to sine of x dx. And then the derivative of u is 2x dx. And unlike substitution, you actually plug this in. You don't say solve that for x dx. That's something different. Now to find v, we antidifferentiate sine. Sine's antiderivative is negative cosine of x. And so our integral will equal uv, so negative x squared cosine x, minus the integral of v, negative cosine x, du, which is 2x dx. Simplifying slightly, that's negative x squared cosine x plus, I'm just going to take that 2 out, 2 integral x cosine x dx. And as you can see, it's gotten a little bit better, as in we now have x dx instead of x squared, but we're still not at a stage where this is something that we can easily antidifferentiate. So we have to do it again. And on the second one, we're once again going to let u equal x. Du is just dx. dv will be cosine x dx. And the antiderivative of cosine is sine. So now we have negative x squared cosine x plus 2. Don't forget your parentheses. uv x sine x minus the integral of v du sine x dx. And now we've reduced this to something we can just take the antiderivative of. Negative x squared cosine x plus 2x sine x minus 2 times the antiderivative of sine is negative cosine plus c. That double negative makes a positive. And our final answer is negative x squared cosine x plus 2x sine x plus 2 cosine x plus c. And if you have spare time, you could check this by taking the derivative. You'd have to use the product rule on both the first and second terms. But if you take the derivative of this, you should get back x squared sine of x. Now, another tricky thing with integration by parts, and this is something that a lot of you got wrong, so you can pretty much count on it being on your final, is to let the dv be just dx. In this case, u will be sine inverse of 4x. And the reason you have to let u equal sine inverse is because you don't know how to antidifferentiate. You only know how to differentiate it. Its derivative is 1 over the square root 1 minus 4x, the quantity squared, multiplied by 4 because of the chain rule. And the antiderivative of dx is just going to be x. Although that doesn't immediately seem helpful, it should become obvious pretty quickly why it actually is. So this is x sine inverse of 4x. So uv minus the integral of v du. And that 4x quantity squared is 16x squared. So that's the same thing as x sine inverse of 4x minus the integral of 4x over the square root of 1 minus 16x squared. And now, this might not seem helpful, but if you look at that integral and you think about how you might evaluate it, it is doable with a regular substitution. We've already used the letter u, so let's pick another one. Let's pick w. We're going to substitute w to be the 1 minus 16x squared. Then dw is negative 32x dx. And we have just a singular x dx. I'll take that 4 out. So negative 1/32 dw equals x dx. So this is x sine inverse of 4x minus 4 times negative 1/32, the integral of 1 over root w dw. And that can be antidifferentiated just using the reverse power rule. So 4 over 32 is 1/8. This really is w to the power of negative 1/2. And the antiderivative of w to the negative 1/2 is w to the positive 1/2 times 2 over 1 plus c. And then just reduce the fractions and plug back in what w is. And we have x sine inverse of 4x plus 1/4 square root 1 minus 16x squared plus c. And once again, if you take the derivative of your answer, you should get back sine inverse of 4x, provided you make no mistakes in your differentiation process. Now the next technique we learned it's not really a technique, it's just a type of integral. They were trigonometric integrals. And this basically was a combination of identities plus substitution. So for example, if we were asked to integrate cosine cubed x times sine to the 6th, so if we tried to, let's say, u equal sine of x, du will be cosine x dx. But we have cosine cubed here, so if we could only save one of the cosine cubes, like this. So save that cosine x, we're left with a cosine squared x, sine to the 6th x dx. Well, this could become u to the 6th. In this case, this would be the du, and the question is, what would you replace this by? Well, you use the fact that since sine squared of x plus cosine squared x equals 1, that cosine squared x is 1 minus sine squared. And the pattern there is whenever you have a trig function, in this case a cosine or a sine specifically, because the pattern's a little bit different for other trig functions, that has an odd power, that's the one where you pull one off and save it and change the rest into the other trig function. So completing my substitution, I just need to change my bounds. If x is 0, u is 0, and if x is 3 pi over 2, sine at 3 pi over 2 is negative 1. So this is the integral from 0 to negative 1, 1 minus u squared, u to the 6th du. Once you figure out what substitution to make, these integrals actually become pretty easy. So this is the integral from 0 to negative 1, u to the 6th minus u to the 8th du. The antiderivative of u to the 6th is 1/7 u to the 7th minus 1/9 u to the 9th. Evaluated from negative 1 to 0. So that's negative 1/7, actually plus a 9th, and then minus 0. So getting a common denominator, negative 9 over 63 plus 7 over 63 gives us negative 2/63. if you have to substitute for something other than sine or cosine, you may have to save a different sort of amount of something depending on what the derivative of your substitution is. So in this case, it seems like we're going to have to substitute for that tangent of x in the denominator. And its derivative is secant squared x. So from the secant to the 6th x, the numerator, we're going to have to break it up into secant to the 4th x, secant squared x dx over root tan x. So this part's been taken care of. This part is going to be your du. It's just this part that has to change. And for that, you also use Pythagorean identities. You use the fact that tangent squared x plus 1 equals secant squared x. And also notice that secant to the 4th x really is secant squared x squared. So this is the same thing as tangent squared x plus 1, the quantity squared, over root tan x times secant squared x dx. Now making our substitution, that's the same thing as the integral of u squared plus 1 squared over root u du, or u to the 4th plus 2u squared plus 1 all over root u. So u to the 4th over root u, those exponents will subtract. We'll get u to the 7 halves plus 2u to the 3 halves plus u to the negative 1 half. And now anti-differentiate. We'll have u to the 9 halves times 2 ninths plus 2 times u to the 5 halves times 2 fifths plus 2u to the 1 half plus c. And now we'll just insert what our u was, and we have 2 ninths tangent of x to the 9 halves power plus 4 fifths tangent of x to the 5 halves power plus 2 square root tangent of x plus c. The next technique we learned was trigonometric substitution. And this is a different kind of substitution where you actually replace x by some variation of a trig function. So in this case, because we have a squared minus x squared, we let x equal a sine of theta. So in this case, our a is 5. X is 5 sine of theta. And then dx is 5 cosine theta d theta. And the reason this is helpful is because this will simplify once we make the substitution and allow us to take that square root. So we have, let's plug everything in. Inserting everywhere we have an x, we replace it by 5 sine theta. Everywhere where we have a dx, we replace it by 5 cosine theta d theta. So this becomes 25 sine squared theta times 5 cosine theta d theta over the square root of 25 minus 25 sine squared theta. And so that's the same thing as 125 sine squared theta cosine theta d theta. In the denominator, the greatest common factor is 25. And now notice that 1 minus sine squared theta, that simplifies to cosine squared theta. So we have 25 cosine squared theta, which is 125 sine squared theta cosine theta d theta over 5 cosine theta, and now those cosine thetas cancel as well as that 5 divides out, and we have 25 times the integral of sine squared theta d theta. Now to anti-differentiate this, we have to use the half angle identities. It'd be 25 over 2 integral of 1 minus cosine of 2 theta. And we're pretty close to done. 25 over 2 times theta minus a half sine of 2 theta plus c. Okay, now going back to our substitution, we have to take this thing back into x's. So notice that our original substitution was x equals 5 sine theta. So we know that x over 5 is equal to sine of theta. And we also know that theta is sine inverse of x over 5. Now that's okay to replace here, but it turns out you can actually replace this by something that's not a combination of putting sine inverse inside of a sine. And here's what we have to do. You have to use this identity that sine of 2 theta is 2 sine theta cosine theta. And now this is 25 halves times sine inverse of x over 5 minus sine of theta is equal to x over 5. To figure out what cosine of theta is, you use right triangle trigonometry to say that, well, if sine of theta is x over 5, I have a triangle, there's my theta. Sine is the opposite over hypotenuse, meaning the remaining side is root 25 minus x squared because of the Pythagorean theorem. And now the cosine there is root 25 minus x squared over 5. As you can choose to or not to distribute that 25 over 2. If you do, we have 25 halves sine inverse of x over 5 minus x times the square root of 25 minus x squared over 2 plus c. These are legitimately quite tricky, and this one probably is a bit more tricky than I would try to make it on your final, because I think that this identity really is something that you don't use all that often. I don't really want to make you memorize it, so maybe I would give it to you, or you could put it on your note card. Now the next technique that we learned was partial fractions. And this involved mostly a whole lot of algebra and trying to figure out what fractions were added together to make the ratio that you have. And the way you begin to determine that is you start by factoring your denominator, x times x plus 2, and then observing that this had to come from some number over x plus some number over x plus 2. Now we multiply this expression by x times x plus 2, and that gives us x minus 1 equals a times x plus 2 plus bx. And if you're lucky, at this stage you can plug in clever values of x to determine what the values of a and b are. So for example, if x equals 0, we get that negative 1 equals 2a, so therefore a will be negative a half. And if we plug in x equals negative 2, we get negative 3 equals b times negative 2, or b is equal to positive 3 halves. And this tells us that the ratio x minus 1 over x times x plus 2 really came from negative a half over x plus 3 halves over x plus 2. And if you want to check that, you could get a common denominator and add the fractions together, and you're going to get back x minus 1 over the quantity x squared plus 2x. But the reason the form on the right is more useful is you actually know how to anti-differentiate each of those pieces. The first one will be negative 1/2 times the natural log of absolute value of x. And the second one will be 3/2 times the natural log of x plus 2, and then plus some constant c. There are various ways to use rules of logs to possibly simplify that more. We're not going to go there. This is good enough. Now, partial fractions can get a bit more tricky when you have repeated factors or quadratic factors. So this is an example of the repeated factors. You have to look back at your notes, for example, of the quadratic factors. So we start the same way, factoring. So take out the greatest common factor is x squared. And because this x is squared, you have to have one term for just the x plus another term for x squared. Had that been x cubed, you would have needed an additional term for x cubed. And it's completely possible that a might be 0, but the b probably will not be 0 in any case, because then your common denominator wouldn't have been x squared times x plus 2. It would have been x times x plus 2. So if you have a repeated factor, 1 for each power. Now we proceed the same way, multiply by the denominator on both sides, and we end up with a times x plus 2, b times x plus 2, and c times x squared. Now here you're going to have to use a combination of plugging in various values for x and gathering sort of like terms. I think it's easiest to combine them. So plug in x equals 0, that will 0 at some pieces, and we get negative 2 equals b times 2, and that tells us that b must equal negative 1. If we plug in x equals negative 2, on the right we get 20 minus 6 minus 2 equals 4c. So 20 minus 6 is 14, minus 2 is 12, 12 equals 4c, therefore c must equal 3. Now it's just a that we're missing, and there's nothing we can plug in that will make the b's and c go away simultaneously and leave a alone, so we have to resort to a different method. And that method is to distribute out the right side and group terms by powers. So we'll have ax squared plus 2ax plus bx plus 2b plus cx squared. Now notice that we have ax squared and cx squared. So grouping them together, we have a plus c times x squared. For the x's, we have 2a plus b, and our only constant is that 2b. And if this side is to equal this side, then a plus c has to equal 5. 2a plus b would have to equal 3. And that should have an x there. And 2b would need to equal negative 2. We already know, look, you're going to get here that b is equal to negative 1, which we already found. It's really a we need to find, and you can use either of these equations, but since we know c is 3, let's say a plus 3 is 5. A is going to equal 2. You get the same result if you plug negative 1 into this one for b. You'd have 2a minus b equals 3, twice a, minus b, minus 1. Equal 4, and you'd still get that a was 2. Okay, so all that work to do this integral, turns out for these questions, often the algebra to determine what the coefficients are is the hardest part. So this integral will equal the integral of 2 over x minus 1 over x squared plus 3 over x plus 2. Now the antiderivative of 2 over x will be 2 ln absolute value of x. The second portion you use the power rule on. It's not natural log. So it's -1 times x to the -1st over -1, and then plus 3 natural log of x plus 2 absolute valued plus c. So your final answer is 2 ln absolute value of x plus 1 over x plus 3 natural log absolute value x plus 2 plus c. Another sort of groovy trick is this trick around the world, which uses integration by parts. And this is a bit tricky, but it uses integration by parts repeatedly, and we're going to actually end up adding together some integrals, which is a little bit strange. But here you have a choice. You can let u equal e to the 2x, or you could let dv equal e to the 2x dx. It doesn't really matter, but one choice is easier and one choice is harder. If you let u equal e to the 2x, du is 2e to the 2x dx, and you're going to work with whole numbers. If you'd let dv equal e to the 2x, then v will be 1/2 e to the 2x, and you're going to have to work with fractions. So I recommend that first choice. And once you make a choice, stick with it. dv will be sine x dx, and the antiderivative of sine is negative cosine of x. All right, so this integral will equal uv, so negative e to the 2x cosine x. And remember that the integral of u dv equals uv minus integral v du. So we have uv plus the integral of 2e to the 2x cosine x dx. Let's take that 2 out. And we're going to repeat the process. So we're going to let u equal e to the 2x again. dv will be cosine of x dx, and v will be sine of x. So we have negative e to the 2x cosine x plus 2 times uv e to the 2x sine x minus the integral of 2e to the 2x, so v du times sine x dx. And let's distribute that 2 and then discuss what's going on here. E to the 2x cosine of x plus 2e to the 2x sine x minus 4 integrals of e to the 2x sine x dx. And at this stage, I'm going to let I equal the integral of e to the 2x sine x dx. So notice what I have is the integral I is equal to negative e to the 2x cosine x plus 2e to the 2x sine x minus 4 i's. And I can add those 4 integrals to the one integral on the left, giving me 5 integrals. And then I can divide by 5 to find what the value of the actual integral is. So it'd be negative 1/5 e to the 2x cosine of x plus 2/5 e to the 2x sine x, and then don't forget that plus c. But the kind of strange thing that happens with this around the world where you use integration by parts is you end up adding this integral to the integral that you're equal to on the other side, giving you 5 integrals. And you can let that integral be I just to save yourself some writing. In this lesson, in this unit, we also learned about improper integrals. And here's an example. So one example is when one of the bounds is infinite, and we use this idea later on in this class when we use the integral test to test a series for convergence or divergence. So the first thing is that you know how to find a definite integral, so change the upper bound to a number and take a limit as that number goes to infinity. Now, if you integrate this using something like substitution, you have to change your bounds. So just be really careful about that, because when people did not do that on their first exam, they tended to get things wrong. So we're going to let u equal natural log of x. Du is 1 over x dx. If x is e, u is ln of e, which is 1. And if x is b, u is ln of b, which is a weird thing. So we'll integrate from 1 to natural log b, 1 over square root of u. Or that's the same thing as u to the negative 1/2. And so the antiderivative of u to the negative 1/2 is u to the positive 1/2 times 2, evaluated from 1 to natural log b. If you did not change your bounds to u values, you'd have to go back to x's and plug those original x's in. Limit as b goes to infinity, 2 square root ln b minus 2 square root of 1. Well, this will go to infinity because natural log of b goes to infinity, and rooting it still goes to infinity. So this integral diverges. With some improper integrals, it's not quite as obvious why they're improper, but another instance is when you have a discontinuity in your function. So notice here is that this function is discontinuous at x equals 2 because the denominator is 0. And our interval is from 2 to 3. So we've got to figure out what happens as we go at 2 from this side. So in this case, we take a limit as b goes to 2 from the right, because we're looking at numbers that are slightly bigger than 2. So b to 3, 1 over root x minus 2 dx. And this one doesn't really even need a substitution to anti-differentiate it, so I'm not going to bother. This is x minus 2 to the negative 1/2. Its antiderivative is 2 x minus 2 to the positive 1/2. If you choose to do a substitution, just change your bounds and you'll be just fine. You should get the same thing. So this gives us the limit as b goes to 2 from the right. We'll have 2 times the square root of, well, 3 minus 2, or 1, minus 2 times the square root of b minus 2. So since b goes to 2 from the right, b minus 2 is always going to be positive. That means that you've got numbers that are a little bit bigger than 2. Numbers that are a little bit bigger than 2 minus 2 will give slightly positive numbers, meaning you can actually square root them. So this will actually end up being 2 minus 0, or 2. So this integral converges to 2. So in questions like this, a big thing that I'm checking is I'm checking to see if you can identify what the discontinuity is and which direction your limit should come from. Should it come from the left or from the right? The final unit we had in this lesson dealt with finding approximations for integrals, definite integrals, because sometimes it's not possible to actually integrate this function. So the first one was the Trapezoid Rule. And the Trapezoid Rule's basic principle was you had some kind of curve and you approximated it using trapezoids, so straight lines between the 2 points. This ended up being the average of the left and right sum. And remember that when you find left sums, you plug in all of the left endpoints of your subintervals. When you find a right sum, you plug in all of the right endpoints of your subintervals. And then you average them, so you divide by 2. So we want to estimate this integral with n equals 6. So first let's figure out how wide are subintervals. So delta x will be b minus a over n, so the length of your interval divided by how many pieces. So 3 minus 0 over 6, or a half. So my intervals are 0, 0.5, 1, 1.5, 2, 2.5, and 3. So if I did the left sum, I'd plug in this, 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 and this. If I did the right sum, I'd plug in 0.51, 1.52, 2.5, and 3. So what this trapezoid rule will be, our notation was t sub 6. Each box will have width delta x. We have a divided by 2 because of the averaging. And then first we plug in 0. Then we actually plug in 0.5 twice, one for the left sum, one for the right sum. Then we plug in 1 twice, same reasoning. Plug in 1.5 twice, plug in 2 twice, plug in 2.5 twice, and then plug in 3 just once for the right sum. And my delta x is 1/2, so 1/2 divided by 2 is a quarter. And then just plug those numbers in and simplify them as much as you can. So we're plugging them into the function f of x equals e to the x squared. So e to the 0 will be 1, plus twice, no, 0.5, 1/2, 1/2 squared is a quarter. So 1/2 e to the quarter, plus 2e. Easier to think about 1.5 as 3/2. That will be 2e to the 9/2 once it's been squared. 2e to the 4th. 2.5 we can think about as 5/2. That will be 2e to the 25/4 plus e to the 9th. And obviously that's really as far as you can take it without a calculator, so that is good enough. If you had a calculator, you could get a decimal approximation of that, and that would be an estimate of the area under your curve. Now another technique is the midpoint rule. So in this case, you take your interval. We're still going to divide it into 6 pieces. So those were 0, 1/2, 1, 1.5, so 3/2, 2, 2.5, 5/2, or 3. And then instead of plugging in left endpoints or right endpoints, you plug in points in the middle. So the middle point here will be a quarter. The middle point there will be 3/4. The middle point here will be 5/4, and then 7/4, and then 9/4, and 11/4. In this case, all we do is we find the width of each box multiplied by the height of each box. Well, the width of each box is still delta x, or 1/2. And then we plug the middle points into the function. And the advantage that this method has when you use it is, say, that is your middle point. When you plug that into your function, you end up sort of both getting a little bit of an overestimate and an underestimate at the same time. And it turns out this method's actually pretty accurate. So we'll have f of a quarter first, f of 3/4, f of 5/4, f of 7/4, f of 9/4, and f of 11/4. And then plugging everything in, we have 1/2 times e to the 16th plus e to the 9/16 plus e to the 25/16 plus e to the 49/16 plus e to the 81/16 and plus e to the 121/16. And the final rule that we had is Simpsons Rule, and this rule, we didn't really prove it, but we just discussed what it was and what the pattern was. So the general idea here is that you have a curve on an interval, and you approximate that curve, instead of using a straight line, using parabolas. And the idea, this is actually a pretty accurate estimation technique, but proving what the pattern is a bit tricky. So the first thing for Simpsons Rule is that you have this delta x is divided by 3. And where that comes from is the fact that these are parabolas, and in the derivation, this is what comes up. And then the pattern in the coefficients is 1, 4, 2, 4, 2, ends on a 4, and ends with a 1. So it's tricky. The thing is that also comes from the fact that these are parabolas, and when you fit the parabolas, you get those numbers. Your book does it, it's tedious, and you just have to be able to use what it says. So this says you'll have 1 f of 0 plus 4 f of 0.5s, or 1/2, plus 2 f of 1s, plus 4 f of 1.5, or 3/2, plus 2 f of 2s, plus 4 f of 5/2, and then your last term was 3, and there'll just be one of those. And so notice how you have one of the first, one of the last, kind of like the trapezoid rule. And then these numbers in the middle, the coefficients go 4, 2, 4, 2, 4, 2, 4. They start and end with 4 and flip-flop 4, 2. All right, so our delta x is still 1/2. 1/2 divided by 3 is a 1/6. F of 0 will be 1, plus 4e to the quarter, plus 2e, plus 4e to the 9/4, plus 2e to the 4th, plus 4e to the 25/4, plus e to the 9th. And so there's your estimate for Simpsons Rule. And this is a good method for estimating the area under a curve. It's just that the derivation of it is a little bit tricky.